So we were discussing the image transforms, and we were left with this kind of an example where we said that if we alter the basis for the representation of an image or any kind of this signal, in fact, it could even be continuous time signal, but the concept is the same. By altering the basis for the representation, we may come up with better efficiency. The original way of representing an image was using the raster scan ordering. The raster scan ordering is putting a pixel to be equal to 1 in a raster scan along the row. Then we go to the second row along the column, in the second row along the column, in the third row along the column. So pixel by pixel representation, it's like a representation of a signal using a linear combination of impulses or unit samples. But that is the time basis or the space basis in images. But in linear algebra, from linear algebra, we know that we may have better basis. And the basis that I recommended for this particular case was this. 1, 1, 1, 1 is the first basis. It's like, and with a 1 over 2, it's like having an average DC component or something like that. The second basis image is half ones, half minus ones horizontally. The third one could be half ones and half minus ones vertically. And the final one is like a checkerboard, diagonally ones and off diagonally minus ones. And when we do that, it's always possible to find the coefficients that multiply those new bases. Y11 is the coefficient which will scale 1 over 2 times 1, 1, 1, 1. So what is Y11? It's the inner product of the input X with the basis. And that's possible because the basis that I'm telling you is a proper basis, which means they are orthonormal. They have unit norm and they are orthogonal to one another. If you can construct such a basis, it's easy to find what Y11 is. Otherwise, it would be a little bit more difficult, but of course, it's always possible to find the solution. The solution is like 4 equations with 4 unknowns, and you solve for it, and you can still find what is Y11, what is Y12, etc. Now, the important thing for this case is the distribution of Y11, Y12, Y21, and Y22. And as you see, a majority of the energy or the high magnitude values are condensed around usually smaller frequency components. What do we mean by smaller frequency? For example, 1111 is a DC frequency, it's the smallest frequency. And the others are gradually becoming higher and higher in frequency. And the values are becoming smaller and smaller. So what? If those values are becoming smaller, how can we use them? I claimed that in the previous lecture. I claimed that if you don't use some of these coefficients, if you just crop them away, chop them away, then the amount of error that you make will decrease less. Of course, they will decrease. The representation fidelity will decrease, will be deteriorating, but the decrease will be small. For example, if in the pixel-wise ordering, the pixels, we have some small pixel values. It's a very small image, 6, 10, and 8, and 12, as you see there. So these are the pixel values. Suppose that you get rid of the last pixel value, which is 12, and then the amount of error that you make, which is the difference between 6, 10, 8, 12, and 6, 10, 8, 0, the difference between that. Squared difference, mean squared difference. would be 144, right? It's dramatic. If you further eliminate, let's say, the one at the top of it, which is 10, then it will be 100 times 144. Sorry, plus 144, which is 244. If you further get rid of 8, it will be 64 more than that, etc. It's going on like that. So you're making a lot of errors. It's like considering an image compression, and you have a large image, and you want to compress it by getting rid of some of the portions of the image, because you cannot pass those bits or pixels on the bandwidth. Your bandwidth is not sufficient for transmitting all this data. You don't want to do that. Why would you do that? If you get rid of some of the portion of the image, you lose the image. So you don't do it that way. You do it by converting or transforming into a new domain like this one, where the new representation becomes like this: 18, -2, 4, and 0. And one by one, you can eliminate first, for example, 0. But what would you substitute that elimination with? With another 0. So that means you didn't make any mistakes. You replace a 0 with a 0. So you don't make any errors. So the mean squared error will be still 0. You won't have any error. Suppose you further eliminate -2, the one at the top of it. I claim that the amount of error that you make will be the square of it, which is 4. But is it correct? Let us see. I said it is so. And when you rotate, when you think of the transformation of bases or alteration of bases as a rotation of axis, you will understand that the elimination of each of the axes, each of the bases, would correspond to its square times, its square many distortion. So the distortion will be -2 squared, which is 4. But is it correct? Let us at least do a few examples. For instance, that corresponds to eliminating this one and this one. So it means we are reconstructing our signal using only this and this. Let's do it then. What was y11? It was 18. 18 times 1/2 times 1, 1, 1, 1. This is one coefficient, and it's going to reconstruct an image. Plus y21, which is -4 times 1/2 times 1, 1, -1, -1. And the others are 0. We chop them off. So what is the image that is reconstructed from here? First of all, it is 9 times 1, 1, 1, 1 -2 times 1, 1, -1, -1. So it is, let's write it in a larger box, pixel by pixel. The top left corner is 9 -2, which is 7. Top right one is 9 -2, which is 9 plus 2, that is 11. And the bottom left corner is 9 -2, which is 7. The bottom right corner is 9 plus 2, which is again 11. So this is our reconstruction. All right. By this much of information, this is the image that we can reconstruct. What was the original image? It was 6, 10, 8, 12. Let me draw it in red. It was 6, 10, 8, 12. 12. This was the image, the original image. And by compression, I get this. So what is the squared error between those? What we have to do is we have to term by term, or in the original coordinate location, pixel by pixel differences I have to take their squares and then add them up. The top left difference is 1. Its square is 1 again. And the top right difference is 1. Its square is 1. The bottom left the difference is 1. Its square is 1. And the bottom right difference is 1. Its square is also 1, which makes 4. Now look at this 4 and this 4 that I'm indicating. They are the same. Did we need to make this kind of a reconstruction to see that the mistake that we make is essentially 4? Actually, no. This is always valid as long as the basis that you're using is orthonormal. Just to convince a little further, let us also eliminate this one. Let's not use that either, this one. So the reconstruction from there will be, even without this one, it will be only consisting of one single item, which is 9, 9, 9, and 9. That would be my reconstruction with only one term, which is the DC term, by the way. But the original image was this. So how much error do I have now? The error that I have is the differences between each pixel at their own coordinates. So this difference between 9 and 6 is 3. So the error is 3 squared, plus this difference between 9 and 10 is 1 squared, plus 9 and 8, the difference is 1 squared, plus 9 and 12, the difference is 3 squared. So it is 9 plus 1 plus 1 plus 9, which is 20. See how much error that I made by eliminating those two coefficients, 20. So things are very consistent with each other. We have verified the fact that the amount of distortion that we make after making an orthonormal transformation is the same as the coefficient that we are losing, or the square of the coefficient that we are losing. If we are losing a coefficient of 0, then we don't make any errors. If the coefficient that we are losing corresponds to -2, then the distortion that we will make will be -2 squared, which is 4, etc. Goes on like that. This is the fundamental idea of why we are using transformation in at least image compression, for instance. Image compression is a good application of transformation, but it's not the only application. We can do a lot of different transforms for many different purposes. For example, we know that if you take the Fourier transform, it not only helps you compress signals, by the way, it's very good for compression. We will explain it in near future, maybe today, but probably not today. No, it's going to be next week or the week after that. But it also helps for analyzing the signal, for seeing some periodicity. For example, in your exam question, you will notice that I have given you some images and I have given you corresponding Fourier transform shapes, and I want you to match them. Matching them will help you to develop an intuition in a way that if you look at the Fourier transform, you will understand some of the flavors that it contains inside the image. Does it contain this kind of a line, for example? Does it contain this kind of a periodicity along any direction, etc.? So Fourier transform is a very beneficial transformation. It is the most useful one, not only for compression, but also for analysis purposes. But we have infinitely many transforms. You can just rotate the axis in any way you want, and still that would correspond to a different basis representation corresponding to a different transform. So you can design actually your transforms. But for images, we are left with some typical transforms, and we will also see a methodology to optimize the transform according to an optimization criteria. And all of the things that we are going to do will be unitary transforms. Why is it so? Whatever. Maybe I should use a thicker version. Okay. Unitary transforms, or equivalent to orthonormal transforms. I want to restrict our class of transformations with the unitary or the orthonormal case. The others are also available to us, but the mathematics behind those would be a little bit involved and tricky. It's not going to be as easy. For example, when you get rid of some of the coefficients for compression purposes, if you chop off some samples, the distortion that will be made by chopping them off will not be the same as, or will not be evaluated as the squares of the chopped off terms. It will be different. You have to reconstruct and measure how much error that you make. You have to do that in that case. But nevertheless, the orthonormal transforms is a big class of transforms, and it's still good to know them. Fourier transform being one of them, and discrete cosine transform being another, for example, because it is the most useful transformation for image compression. It is used in JPEG image compression, which is the standard way of doing things. So, what are the properties of unitary transforms or orthogonal or orthonormal transforms? The first one is this: if A is an orthonormal transform or a unitary matrix, and U and V are vectors, U is the input vector, V is the transform output. You can think of it like that. It preserves energy. The norm of square norm of V will be equal to, let us also show it, it's going to be equal to A times U square norm, and that is equal to U conjugate transpose, U conjugate transpose times A conjugate transpose, which is the conjugate transform of A times U and A times U itself. Okay, this is the square norm. If you take the square root of this operation, it will give you the Euclidean norm. Because how do we find the norm of a vector? We take the inner product with itself. I'm taking the inner product of V with itself, which is V conjugate transpose times V. Of course, we are generalizing the fact that U and V, and therefore A, could contain complex numbers. It doesn't have to be. They don't have to be real values. Now, here, notice this term, A conjugate transpose A. And from the definition of a unitary matrix, if A is a unitary matrix, then this is identity matrix. Okay. And when you insert an identity matrix between a row and a column vector, that means you can just get rid of that identity. It's equal to U conjugate transpose times U, which is the square norm of U. So what we discovered is the square norm of V is equal to the square norm of U. Therefore, this kind of a transform, the A transform, if it is a unitary transform, will be preserving the energy. This one is also known in in Fourier transform, from signals and systems, you may remember, to be called the Parseval's equation. We know that the total energy in Fourier domain is the same as the total energy in time domain. This is the reason for that. The second we can think of, let's consider random vectors, because to apply to a signal, we have to assume that the signal is a random signal. Otherwise, if it's a deterministic signal, you don't really need a transformation, because the deterministic signals are there, you know it, and there's no reason to compress it. You can just say it is it can be indexed. It's the first image you say, and the first image is known, so I don't need to compress that image. I can tell the other guy that it's the first image. It's against the idea of telecommunications, the idea of uncertainty for the requirement of telecommunication. If it is deterministic, you don't communicate. So we have to think of random signals as well. And whenever we are thinking of random signals, we have to make new definitions. For instance, the square norm of U for a random vector U is not directly equal to U conjugate transpose U. It's not only this, but it's the expected value of it. We have to state it like this. So making things random and suitable for telecommunications is easy. You just put an expected value operator to the left of it, and it means it's working for random signals. So with this kind of a definition of the square norm, then and some other definitions, for example, the mean of U can be expressed as the expected value of U, and the autocorrelation of U, which is a matrix, is again the expected value. We have to put the expected value of U minus its mean times U minus its mean conjugate transpose. Notice that whenever we say U underscore underbar, we mean a vector for lowercase letters at least. And whenever we mean a vector, that vector is a column vector. So when you multiply a column vector with a row vector, you come up with a matrix. If you multiply a row vector with a column vector, you come up with a scalar value. Okay, so this one is a matrix. Now, I have been using conjugate transpose operators all the time. For example, here. Let me put an exclamation here and warn you about implementation using computers. If you are using MATLAB, when you say a transposition, which is usually notated with the trend function, or if you put a prime, it also takes the transpose. When you take the transpose of a vector, MATLAB automatically takes the conjugate transpose. Okay, it already means this one. You don't have to conjugate any further. Transpose is conjugate transpose in many mathematical tools, including MATLAB. If you don't want to put the conjugation, and if you only want to take the transpose of the vector, the real actual transpose, then unfortunately unfortunately, you have to transpose and then conjugate again to make it not conjugate transpose. In MATLAB, therefore, conjugate transpose is automatic. When you say transpose, it means conjugate transpose. Now, these are a few definitions of random. With these definitions, what happens to the transformation of the random vector U is the question. Now, for example, what is, oops, sorry, red, let's make it black. What is, for example, mu V, the average value of the transformation output? That is, of course, expected value of V, and that is expected value of A times U. Now, in an expected value operator from random processes or things like that, you may remember that anything that is a scale, which is not random, which is not the signal itself, can be taken out of the expectation operator. So it's this. A times expected value of U, and we know that expected value of U is mu U. So the answer is A times mu U. Let me say this is equal to mu V. So this is our first observation. The average is also transformed with the same transform. If the signal is being transformed by A, then its average is also transformed by A. Now we have to proceed to the autocorrelation. By the way, the autocorrelation that I am writing just on top of that is essentially not the autocorrelation, but the autocovariance. I was making a mistake at that point. The autocorrelation RU does not use subtraction of the mean. So this is essentially incorrect. This is not. Sometimes people just use correlation and covariance interchangeably with the assumption that the mean of the signal is 0. So if the mean value is 0, then autocorrelation and covariance are the same. Or if you just subtract the mean and make it a 0 mean signal, then autocorrelation and autocovariance would be the same. But technically speaking, there is one difference like that. So we are talking in terms of autocovariance. So CV, the autocovariance of V, what is that equal to? It is the expected value of, this is going to be a little bit long, but nevertheless it's going to work out. V minus mu V times V minus mu V conjugate transpose. This is the autocovariance, and that is equal to expected value A times U minus A times mu U, because I know that mu V is equal to A times mu U. I just found it at the top. And the conjugate transpose of it, A times U minus A times mu U, altogether conjugate transpose in an expected value. And that is equal to expected value of A times U minus mu U, to combine everything in a parenthesis form. And the right-hand side is A times U minus mu U's conjugate transpose. When you're taking the transpose, their orders change. So first I have U minus mu U conjugate transpose, and then A conjugate transpose. When I take the conjugate transpose of the combined term, which tells me that, indicates me that this A can be taken out of the expected value from the left-hand side, and this A conjugate transpose can be taken out of the expectation from the right-hand and that is A times expected value U minus mu U minus mu U conjugate transpose. And at the right hand side, I have A conjugate transpose. And I know that this thing that I have in the middle is CU. So the answer is CV is equal to A times CU times A conjugate transpose. It was a little bit cumbersome, but this is an important observation. So the covariance or the autocorrelation or autocovariance, they both obey this rule. If your signal is transformed by A, then your covariance matrix is multiplied by A from the left-hand side and A conjugate transpose from the right. It's not as simple as what is happening to the mean, because mean is transformed with the same matrix A. It's simple, but this one is slightly more involved. Okay. Before giving a break, we can talk about a few example transforms. And the first example transform that we will be talking about is the finite transforms I'm talking about, like the transforms in the form of multiplication with a matrix, because we will have a finite discrete signal starting from 0 going to some time limit, or a finite discrete time image, which is a digital image in some sort, with width and height finite. For such things, we are just applying a matrix multiplication, as we all know. And DFT is the first thing that you have to know, which is also known as or implemented as FFT, which means fast Fourier transform. The other one is discrete Fourier transform. They are the same. Fast Fourier transform is the fast implementation of DFT. So it's not a separate transform. But in MATLAB, for example, again, talking about that tool that you may be using, we don't have DFT as a function name. Instead, it uses FFT. It means DFT. Actually, it's just making a fast implementation. Now, the DFT, we know what it means. They are the samples of discrete time Fourier transforms. They are the samples of DTFT. And that is also equal to, within one period, the values of the discrete time Fourier series. Because we know that if your signal is periodic with period n, then it has n Fourier series coefficient. Okay. These n Fourier series coefficients are equal to the DFT of length n version of that signal. So you can also think of it like that. So that's the tool that we use for approximating or for interpolating discrete time Fourier transform. Discrete time Fourier transform is not a discrete to discrete transform. It's a discrete to continuous. You have a discrete signal, and its discrete time Fourier transform is a continuous function of frequency omega, which is periodic by 2 pi. Right? So that's different. You have to sample that 2 pi period into n instances and take those n samples that would correspond to the n point DFT of your original signal. And it can be implemented using a matrix multiplication in one dimension, of course. If you have a vector as an input, then that vector times this matrix would give you the DFT, where the DFT is, the DFT matrix is 1 over square root of n, that n is the size, the DFT size, e to the minus j 2 pi over n, k, n. What is k and n? K and n are the coordinates, the column and the row of this F matrix. So F is an n by n matrix, n times n matrix. And you render each item like this, it would make a DFT matrix. So if you have, for example, U as the length and input vector, then DFT of U is equal to V is equal to this F matrix times U. This is how we make the DFT. F V is equal to F times U. The 1 over square root of n is an arguable coefficient. I put it deliberately to make this DFT to be orthonormal. I'm not sure in the implementation of MATLAB they have 1 over square root of n. But if you don't use 1 over square root of n in DFT, for instance, then when you are taking the inverse DFT, you have to put a 1 over n. Or if you put a 1 over n in taking DFT, in the inverse DFT, you don't put anything. So that the DFT and inverse DFT are normalized in multiplication, are normalized with a 1 over n. And in order to make it orthonormal, completely symmetric, I assign 1 over square root of n to one side and 1 over square root of n, which is the same, to the other side, to make them having unit norm, both of them. Otherwise, if you're reducing the norm at one side, you have to increase the norm in the reconstruction side. Or if you increase in the transformation, you have to decrease in the reconstruction. This is the proper way of doing the discrete Fourier transform. Okay, let's indicate a few properties of this discrete Fourier transform. It's a nice one, but you have to use it with care. First of all, it's in image processing. Visualizing the DFT does not really help you much for looking at the Fourier transform. For instance, if you have an image of a person, okay, and you want to take the Fourier transform, you expect to see something like this. In the center of omega 1, omega 2 axis, in the center, there's a peak because that's the DC value, and towards the sides, to higher frequencies, it decays. Or let me try to illustrate it on 2 dimensions. It's like you have a peak here, and the values are decreasing towards the tails, like this. Okay, there's a peak at the top. In magnitude, of course, it is complex valued, but in magnitude, we expect this kind of a situation over the omega 1 and omega 2 axis. Unfortunately, that's not what you observe, and this is 2 pi periodic, by the way. The same kind of a peak appears at 2 pi periodicity, like this. But when you take the DFT, what you start observing will be on its own axis, or in a parametric axis, the same size data, the size of images, let's say n by n. This DFT is also n by n. But from these corners, you start seeing some high values, and those values are being decreased into the center. Or if you want to visualize it in 3 dimensions, here you have a peak, and it decreases, and then it increases again, and decreases, and then increases again, decreases and increases again, decreases and increases again. Some shape like this. You see, the corners are a little bit upward, and at the center position, somewhere around here, it has the lowest. This is because using normal DFT, we'll assign this 0, 0 position to be not the DC value. Sorry, to be the DC value, and it goes on only in the positive direction. Whereas in the Fourier transform, the DC value is in the center, and to the left and to the right of it, we are still capable of plotting something. But this is not a plot like that. This plot is only on the positive quadrant. So when you plot it like this, or when you make a 3-dimensional rendering of this Fourier transform, either this one or this one, this is quite undesirable. People want to see the DC term, or the 0 frequency, in the center of the image, as if the left part of it is negative frequencies and the right part is positive frequencies. Similarly, top is positive and bottom is negative frequencies. So how are we going to do that? When you take the DFT, it looks like this, but actually it is a continuation of a presumable thing like this. So you see, you want to crop it from here, or in a similar manner, what you can do is you can take these parts and put them here like this. Repeat them, and then take these and put them to this quadrant like this, and take these and put them here. It may be a good idea to use different colors if you wish. Let me try to do it that way. You have a DFT. This is the black. This is the red. This is the green. And this part is the blue. Okay. Let me start with the blue. It's here. The red is here, and the green is here. So it looks like this, and then you crop the image to reproduce like the dashed one, like this one. You see, you have now a new image, and that new image is showing that the DC point in the center, and towards the tails it is decreasing. That's the more natural way of people looking at the Fourier transform of 2-dimensional images. And the way to do it, or there is a command in MATLAB, for example, from here to here, it is called FST shift. I think this is FST shift 2 because it is in 2 dimensions. If you use this command, it automatically makes these adjustments for you and makes a visualization. So if you're working with MATLAB after taking the FFT, when you want to plot the absolute FFT, you have to take the magnitude and then plot, because it's complex values. And if you try to plot any complex values function, you know that it's a problem, so don't do it. You use FFT shift. You usually do it like this. You say image or mesh is a better thing. Let me erase this. Use mesh FFT shift 2 FFT 2. No, before that I have to use the absolute value. Absolute value FFT 2 of image. Or let's use a different thing, because image is a command, so the variable name should be different. Let's say my image, where my image is a grayscale image that you have, for example, the Lena image, the cameraman image, etc. You take its FFT in 2 dimensions, it's FFT2. It's just applying along the rows and the columns, separable transform format. And you take the absolute value of it, and then you use FFT shift 2. That would give you the dashed shape. That's how you take the FFT, find Fourier transform, the fast Fourier transform. So essentially, it's like it's a periodic thing. There is a 2π periodicity or n periodicity going on in 2 dimensions, and you are cropping in the Fourier domain. You are cropping either from here, the solid line, or from the dashed line, from here. It's like cropping from there, and it indicates that x tilde -1, for example, is actually the same as x tilde capital N, because here the green corner is the same in both the dashed and the solid line images. So this kind of equality holds in the Fourier transform, in the discrete Fourier transform in DFT. The DFT of x of n1 and 2, which could be noted as capital X of k1, k2, you can say. From here, I say that is essentially periodic, intrinsically periodic, and the periodic extension of that is what I call capital X tilde of k1, k2, and that's what I am using at this point. Okay. There are a lot of properties that hold for the discrete Fourier transform, like convolution versus multiplication and things like that. But since this is periodic, if you multiply 2 signals, like x1 of n1 and 2 times x2 of n1 and 2, that would make the DFT to be corresponding to a convolution of x1 of k1, k2, and x2 of K1, K2, but I have to put, by the way, it's a two-dimensional convolution, so let me put 2 stars, and then I will put circles around those stars to indicate that these are circular convolutions. Do you know what a circular convolution is? A linear convolution, we know we have a signal, we have another signal, we flip around one of the signals and slide over the other one, make multiplication. Now, in periodic convolution, you again flip around, but during the overlap, this much overlap with my with these fingers that I have, except for those, the other fingers that I have here are actually folded from the other side and they enter into the same signal. So you are sliding one signal, but while sliding, you take one sample and put it to the left-hand stack, and then shift more, and then put another and put it to the left-hand side. Take another from the right-hand side, put it on the left-hand side. So that is circular convolution. It's not like linear convolution where the slide may overshoot to the extended part to the right or to the left. In circular convolution, these extensions may not extend to the right or to the left. They must be folded back into the signal. Okay. Please, if you're uncomfortable with this circular convolution, please search for it and try to understand. Because it's important when you're multiplying two signals, the convolution is not linear, it's a circular convolution. Some kind of, you can also say it's like periodic convolution. This is also a possibility for indicating. Or you may also visualize it like this. You make one of these x1 or x2 Fourier transforms periodic. You take replicas, and then when you take the convolution with that periodicity, that automatically corresponds to circular convolution. Please try to exercise a little bit on this one to understand what these really respond to. Now, the Fourier transform can be implemented separately, horizontally, and vertically alongside the image. That's quite a common way of doing it. And there is a fast implementation of it, which is also known as the fast Fourier transform. Since DFT is very thoroughly investigated in digital signal processing, I don't want to go into further details of that. And I want to stop at this point. And then, because I want to talk a little bit about the discrete cosine transform, which is a more dedicated transform for image processing, particularly image compression. So I want to go into that. And before going into that, let's give a break. Let's meet at 11 o'clock. It's 10:30 already. So let's meet at 11 o'clock. We will do one more hour, starting from discrete cosine transform and some other transformations. We will be looking at more dedicated transformation. Next week, in the class, we will see how to optimize the transformation, which is a very nice and good way of looking at the transform phenomenon. So I strongly recommend that you come to the class next week. Okay, that would be a very critical class. But now we will meet at 11 o'clock to cover some essences of discrete cosine transform and some other typical well-known transforms. Therefore, I'm stopping the recording right now.